In section 3.1, we're going to look at quadratic functions a little more in depth, and then as we progress through chapter 3, we will look at polynomial functions, things where our exponent is higher than being raised to a power of 2. Now, if it's a polynomial function, we are going to write out what the actual definition of a polynomial function is. That occurs here in the center of the page, and you would see that if we were to put our first term raised to whatever the highest exponent is in descending order, A stands for our coefficient, and we have these exponents that are now decreasing one by one until you eventually get to the point that you would have a x to the first power plus whatever constant you have raised to the 0 power. And anything raised to the 0 power is 1, so it would end up just being whatever that constant is. Now, there are special names that are associated with certain polynomial functions. We're going to fill this out just to be familiar with the vocabulary, again, knowing that vocabulary is an important part of algebra. And if you look at the first one, it says f of x equals 2. You do not see a variable at all in that function, and that means it is a constant. So if I do not see a variable, if it's just f of x equals some number or y equals some number, it's a constant function. And the degree is always indicated by whatever the highest exponent on a variable is within my function. And if I don't have a variable that I see, it's because the exponent was 0. And the leading coefficient would be whatever that number is that would be in front of the highest variable to the highest exponent. The only thing I have here is 2. That will be my leading coefficient. Now, if you look at the next example, f of x equals 5x minus 1, you should recognize this as being linear. We have something that is x to the first power, no variables in denominators, no special symbols. And if I were to ask you what would be the exponent on that variable x, hopefully you would be able to tell me it's 1. So that means it's a first degree polynomial. And the leading coefficient will be whatever that coefficient or that number is in front of x. In this case, it will be 5. Next one is the one we'll spend our time talking about on this lesson, which would be the quadratic. And we know it's quadratic because it has the x squared as the highest degree. So that would mean that variable has an exponent of 2. That makes it a second degree polynomial. And the leading coefficient will be 4. Now, in the next polynomial function, we would see that the highest degree that we have here, the exponent that is the largest, is a 3. It's x to the third power. That means this is a cubic function, so it would be degree 3, and that leading coefficient is 2. The last one that we have is something where the largest exponent is 4. We could call it a quartic function. That would be the specific name, but I will tell you, if you have to give a name to anything that's higher than a cubic, you can just call it a polynomial function. You don't have to keep learning a lot of specialized names. It's fine to just call it polynomial. The degree is 4. And the leading coefficient, remember, if I don't see a number in front of that x to the 4th, the coefficient is actually 1. Now, as we talk about these quadratic functions, we know that we have something that's quadratic as long as f of x is equal to ax squared plus bx plus c. Remember, we looked at this before when we discussed the quadratic equation formula. That means this is in standard form when we get everything on one side of the equal sign. And as we said before, a, b, and c are real numbers, but the a value cannot be 0, because if that happened, that would mean that we wouldn't have an x squared term, therefore it wouldn't be quadratic. Now, we're going to add another form for quadratic equations in this section, and it is called vertex form. And that's what we see here. F of x equals a times, and then in parentheses we have x minus h squared plus k at the end. Now, because we talked about all those transformations in Chapter 2, there are some things that we should recognize here. The a value that's in front of our parentheses, we already know all of this information because of those transformations. We know if it's a positive number, this parabola will open up. If it's a negative number, the parabola will open down. We also know if the number is greater than 1, we have a vertical stretch. But if the value is between 0 and 1, we have a vertical shrink. The other thing that will be helpful for us to realize is the h and the k represent horizontal moves with the h. It moved either right or left, h units, and the k would represent vertical moves, either up or down, k units. Remember, the parent would have the vertex at 0, 0. So if I'm looking at an equation that's in this form, the reason we call it vertex form is because my vertex will be at the point h, k. And that is very valuable information, because remember, when we're graphing a parabola, when we're graphing an equation that's quadratic, we need to know where the vertex is, and then we're going to need additional points, but the vertex is very important. So what we're going to do is learn how to graph these functions both in standard form and in vertex form. So if you look at equation A, f of x equals x squared plus 4x minus 4, in order to graph this, we do need to know where our vertex is. But it's in standard form, and when it's in standard form, I don't see the vertex in the equation, so I need something to help me. An important piece of information about a parabola is that our vertex is located on an axis of symmetry. In other words, we have symmetry with a parabola, and if I fold the figure through the vertex, the two halves will match up. So that line of symmetry is extremely helpful when I get ready to graph. And in order to find the axis of symmetry, I need a little equation to help me out. And this equation is x equals negative b over 2a. Now that should look a little bit familiar, because that's part of the quadratic equation formula. Not a coincidence. That's going to help us to find where our vertex is. So just like if we were using the quadratic formula, when it's in standard form, we're going to identify the a, in this case it's 1. We need to know b, which is 4. And I will go ahead and write down the c, even though I don't need it for the axis of symmetry. The c is negative 4. Now, one thing that's important, since the axis of symmetry is an equation, please do not leave off the x equals. We're not just looking for a number. The equation will be the vertical line that is passing through the vertex. So if I were to plug in the value that we found for b and the value that we found for a, b is 4, a is 1. And when I clean that up, I get x equals negative 2, because negative 4 divided by 2 is a negative 2. Now here's what I know from that. That means this vertical line crosses the x-axis at negative 2. So I'm going to put a dashed line at x equals -2, and I know somewhere on that line my vertex for this parabola has to exist. In order to find it, I need to plug this x value into the equation, and then I'll know the y value of the vertex. So my equation is x squared plus 4x minus 4. When I plug in, I'm going to have -2 in parentheses squared plus 4 times -2 minus 4, and that will give me my ordered pair. Well, cleaning up, -2 squared becomes +4, plus 4 times -2 is a -8, minus 4 at the end. That tells me my vertex occurs at -2, -8. So when I go to my graph, -2, -8 is where the vertex is. And I'll put that point there. Now, because there is symmetry, that will be extremely helpful for me to be able to find more points in graph. Remember, with a parabola, we need a total of 5 points, the vertex and 4 more. But think about it, since I have symmetry, if I can find 2 more points, I can reflect those points over my axis of symmetry and find the other 2. So I want to choose something not very far away from my axis of symmetry, and I'll plug that in for x. You probably recognize that 0 is a useful number to plug in. And if I were to do that, an interesting thing will happen. The first 2 terms automatically become 0 because the x is squared in the first term. 0 squared is 0. In the second term, 0 times anything gives me 0. So an interesting thing, this will be very helpful if you learn this, is when I'm in standard form, my c value will always be my y-intercept. So I know that 0, -4 is a point that's on this parabola, and using symmetry means if I move horizontally back toward the axis of symmetry, I had to move 2 units to get to the axis of symmetry. If I move 2 units on the other side, that tells me that the ordered pair -4, -4 is also on my graph. And I don't have to plug in to find it because I'm just using symmetry. Now, I need to find another pair of points. We might see what happens if we use 1 for x. So if I were to plug in 1, square it, plus 4 times 1 minus 4, what I will discover is that I get the ordered pair 1, 1. And I'm running out of room, so I'm going to put it right there. And that tells me that if the ordered pair 1, 1 is on my graph, using symmetry, I had to move 3 units to get to the left to get back to the line of symmetry. If I move 3 more units, then, just a moment, I will be at the ordered pair -5, 1. There we go. And now with 5 points, I can sketch my graph. And a couple of things that you should pay attention to before I even started graphing. If I look at this function, because the a value was +1, positive number tells me this parabola should be opening up. This one is. That's helpful to double check that. It appears that everything is in order, and that will give us a faster way of being able to graph a quadratic equation that is in standard form. Now, if you look at the example for C, technically we could do B either way. We could either use standard form or we could use vertex form. But equation C, if you look at it, is written in vertex form, and that means when we look at it, we should be able to see the vertex in the equation. Remember what we discussed in those transformations. If I look in the parentheses, it is x plus 3 in the parentheses. That tells me that I'm actually moving 3 units which way? I'm moving 3 to the left. That tells me my vertex is at -3. I know I have to take the opposite sign of whatever follows the x, but my vertical translation is exactly as it appears. So that tells me that my vertex is at -3, 5. So at -3, +5, I have my vertex. So I know one point that is on my parabola. Here's the other thing I already know before I've plugged anything into my equation. I know where the axis of symmetry is, because remember that axis of symmetry has to pass through the vertex. So whatever the x value is in the vertex, my axis of symmetry will be x equal to that value. So in this case, x equals -3. And I'm going to put that dashed line because it will help me with my graphing. Now, I'm going to choose some values for x. I will plug into the equation to solve for more points that I can graph. We don't want to move very far away from our axis of symmetry, so we might want to consider trying something like maybe -1 for my x value. You could definitely choose some other numbers and see what happens. While I'm plugging this in, if you were to look at the equation and answer the question, which way should this parabola open, I certainly hope you recognize it's going to open down because I have a -2 in front. So I know I've got a vertical stretch of 2 and it was reflected over the x-axis, so this parabola will open down. Now if I clean up what I have in the parentheses, then here is what I know. When x is -1, I will end up with -2 times -1 plus 3 is a +2, which has to be squared. Add 5 to it. If I put all that together, I get -1, -3. So when x is -1, y is -3. Using symmetry, if I move 2 units to get back to the axis of symmetry, move 2 more units to the left, that tells me that I also have the ordered pair -5, -3 on my graph. So I have 3 points. I need a total of 5. Let's see what happens if we try 0. Now remember, there is no c value on this, so you will not be able to see any other point when you look at the equation. You're going to need to plug in order to solve. So what happens here is if I add 0 plus 3, I get 3. I'm going to square that and add 5 to it. Now, when I square the 3, that's 9 times -2, which is -18 plus 5, and I've sort of pushed the limits on this because that tells me when x is 0, my y value is -13. My graph only goes down to -10. So what I can do is extend it just a little bit, and I'm going to have a bit of an estimation that takes place here. But that tells me if I had the point 0, -13 on my graph, I'm moving 3 units to get back to my axis of symmetry. If I move 3 units on the other side, I would have -6, -13. Obviously, if I had chosen a point like -2 instead of 0, it would have fit on the graph nicely. But you can adjust just a little bit as long as you're not too far out of range. If we had tried to use something like +1, I don't believe we could have found a way to get it on the sheet of paper. So this would give us the graph for this equation when it's in vertex form. We see the vertex in the equation, use it to identify the axis of symmetry, and then we're going to find 2 more points and use symmetry to reflect them and plot them. At the information we have here, we're going to sum up all the things we've talked about. we have standard form written out for us, f of x equals ax squared plus bx plus c. If it's written in vertex form, then we end up with f of x equals a times x minus h in parentheses squared plus k. And there's no reason to memorize an expression for k. Remember, we had to learn a way to find the h value where our axis of symmetry is located. But all we have to do is plug in that h value to the equation. In other words, find f of h. That would be equal to k. So we don't need anything special that we have to learn for that. So again, if we want to change from standard form to vertex form, then we would have a times x minus h in parentheses squared plus k. We do know that the a value can't be 0. If it were, we wouldn't have an x squared involved. We know that the h value is equal to negative b over 2a. And the k value we find if we were to plug the h value into the function. Now, these are some characteristics that we should recognize are true with a quadratic. We do know that the graph will be a parabola. We know where the vertex is. It is at the ordered pair HK. And we know the axis of symmetry is the vertical line x equals h, or x equals negative b over 2a if it happened to be in standard form. Depends on which form we're working with. Now, if the a value is greater than 0, the parabola opens up. But if the a value is less than 0, the parabola will open down. We know that if the a value is between 0 and 1, if the absolute value of a is less than 1, then we know that it is a vertical shrink of the original graph. And if that a value, the absolute value of it, is greater than 1, then that means it's a vertical stretch. So we're including information that we learned back in Chapter 2. The y-intercept is the ordered pair 0, c. Remember, if it's in standard form, that c value will be our y-intercept. And if I asked you to find the x-intercepts, you actually would already know how to do that. You learned how to do that back in Chapter 1 when we worked with the quadratic equation formula. When we were solving for x using the quadratic formula, what we were actually doing is finding the x-intercepts. We were trying to find where would the y value be equal to 0? Where would it cross the x-axis on the graph? So that means if we use x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, we would find our x-intercepts. And if you remember when we discussed the discriminant, the b squared minus 4ac part, here's what we know. As long as it's a positive number, then the x-intercepts will be 2 real numbers. And that simply means, if I gave you a quick illustration of the graph, somewhere you're going to see this parabola cross the x-axis 2 places, whether it opens up or it opens down. That's what happens. Now, if the b squared minus 4ac equals 0, the x-intercept is only 1 real number, and that's because it is the vertex. That would mean if I were looking at the graph, somewhere on the x-axis is where the vertex occurs, and that's the only place that the parabola will touch the x-axis. Now, if the b squared minus 4ac is less than 0, remember back in Chapter 1, we found there were complex solutions, but there are no real solutions or no x-intercepts. In other words, it would either have to be a parabola that opens up, but the vertex is already above the x-axis, or we have a parabola that opens down and the vertex is already below the x-axis. Now, if you look at this next example, let's try to make sure we can interpret what the questions are asking us to find. We have an equation, notice it's in standard form, and it says find the axis of symmetry and the vertex of this parabola. Now, it does say using the vertex formula, but that wouldn't make as much sense for us to do that when we already know how to find the vertex and the axis of symmetry when it's in standard form. So that would mean to get the axis of symmetry, we need that little formula. Do you remember what it is? X equals negative b over 2a. Now, let's look at what we have. What is our a value? It's negative 3. What's our b value? Well, it's 12. So if I come back and I plug in, my b is 12, my a is negative 3, I'm going to have negative 12 over negative 6. So the axis of symmetry is x equals positive 2. Now, in order to find the vertex, remember, I need to find f of 2. I'm going to plug in the x value of my vertex in order to find the y value. So if I were to plug in 2, I'll have negative 3 times 2 squared plus 12 times 2 minus 8. And if I were to clean that up, that's negative 3 times 4 plus 12 times 2 is 24 minus 8. That tells me my ordered pair for the vertex is positive 2, comma, positive 4. And that's all we were asked to find. So that's all we'll do. Now, we're going to discuss quadratic models. These will be real-life examples of things that can be represented using quadratic equations. And we're going to keep coming back to these projectile motion questions frequently. There are a number of things in the real world that you can model using a quadratic formula. Think about with football. If a quarterback passes a football, the shape of the arc of the football really is a parabola. You can represent it with a quadratic equation. If you were to toss something off the top of a building, it would be half of a parabola. It would arc down as you throw it out, and gravity pulls down on it. If you shoot something up in the air or throw something up in the air, gravity will pull it back down, and unless you have shot it straight up or thrown it straight up, there's going to be some amount of arc to it, so it will end up having that shape of a parabola. Now, what I won't ask you to do is to write the equation from the information, but I do want you to recognize how the information that's given to you is represented in the equation. So when you look at this and it tells you that a ball is projected directly upward from an initial height of 75 feet, the initial velocity is 112 feet per second, look at this equation that represents it that's written for you in A. S of t equals negative 16t squared plus 112t plus 75. Here's what you recognize. First of all, the information that they've given us is that the initial height was 75 feet. Look where that shows up. That's my c value in the equation. They also tell me the initial velocity was 112 feet per second. That shows up as my b value. The one thing they didn't tell me anything about is represented in this number, negative 16. Well, because we're measuring in feet per second on the velocity, the negative 16 is actually the force of gravity in feet per second. Anytime that your problem is a projectile problem and your units of measure are feet and seconds, you're going to see a negative 16 as gravity pulls that back down to Earth. If it happens to be in meters per second, you will see a different number there. Now, the other thing we need to know is what these variables represent. We have a t and we have an s of t. The t, I hope you would recognize, stands for time, and that would be in seconds. The s of t, what's the other thing that changes during the course of this problem? Besides the fact that time is ticking along, you have a change in height. This ball is going to be at different heights during this period of time. So I want you to see where these pieces show up in the equation. Now, B is the first question that asks you to find something, and it says, after how many seconds does the projectile reach its maximum height? There is a very important word you need to clue into here, and it is the word maximum. We've worked with projectile questions before, but asking us something about a maximum height is a new question, and the reason is we now have the ability to find the vertex, whether we've been given a quadratic that's written in standard form or in vertex form. And the word maximum or minimum, if I see either of those, is asking me to find something related to the vertex. It depends on whether the parabola is opening up or down. If it opens up, you've got a minimum value where the vertex is, but if the parabola opens down, you have a maximum value where the vertex is. So what I need to figure out is my vertex has two parts, an x and a y part. In this particular problem, I need to ask myself, is the time in the location in the equation I would expect to see x, or is that where I would expect to see y? The time is the x value of the vertex. The height is the y value in the vertex. So when it asks me after how many seconds does it reach its maximum height, which part of the vertex is it asking me to find? The time, which is the x part of the vertex, which means if I were to use that little formula or little equation that we learned earlier in this section, negative x equals negative b over 2a, I would know the time when this ball reaches its maximum height. So let's plug in. If I go back to this equation, the b value is 112. The a value was negative 16. So if I clean this up, I end up with negative 112 over negative 32, and if you use your calculator, you discover that at 3.5 seconds, that is the maximum height. So it takes 3.5 seconds to get to the maximum height. Now there's a second part in this question, because now it says what is the maximum height. So now it's not asking me for the time, it's asking me what would that height be. Well, I need to evaluate f of 3.5 because I need to know the y value at the vertex. This is also a time when you're going to want to use your calculator. So very carefully plug everything in and use 3.5 in place of the t. And when you do that, you should end up with the number 271. And that would be in feet. That is the maximum height. So anytime you see the words maximum or minimum in the question, recognize it's asking you about the vertex. You have to determine, do I need the x part or the y part? Now, C is actually a question that we have already done before. For what interval of time is the height of the ball greater than 200 feet? So what I do know is this is the original equation. It was actually s of t equals negative 16 t squared plus 112t plus 75. If I want to know for what interval would the height be greater than 200 feet, picture in your mind this ball is going up. On the way up, it hits 200 feet. It keeps going up until it hits the vertex. Then it starts to come back down, and somewhere on the way back down, it hits 200 feet again. So visually, that would mean if this thing leaves the top of a building, it's going to do something like this, and maybe right here is a height of 200 feet. I need to know what time it hits it on the way up and what time it hits it on the way down. And the way I'll find it is I will put in that height for my S of t. And guess what I have? I have an equation that I can now set equal to 0 and use my quadratic formula to solve. So if I subtract 200 from each side, I'll end up with 0 equals negative 16 t squared plus 112t. And then if I have 75 minus 200, that gives me minus 125. So now I know that A is negative 16, B is 112, and C is negative 125. You have to be certain you set this equal to 0 before you identify A, B, and C. So now I can plug in to negative B plus or minus the square root of B squared minus 4AC, all of it over 2A. You will want to be very careful that you put this in your calculator correctly. And remember, you're going to need to do it one time with the plus sign and then come back a second time and do it with the minus sign. So if I plug in these values, I'm going to have a negative 112. The first time I put it in my calculator, I'll put plus the square root of, and then in parentheses, do 112 squared, minus 4 times negative 16 times negative 125. I would hit enter at that point, and then you can divide it by 2 times negative 16 is divided by a negative 32. If I do that one time with the plus sign and then I go back and I do it a second time using the minus sign, then what I get for my intervals, if I round to the nearest hundredth, would be 1.39 seconds and 5.61 seconds. That's the interval of time that the ball would be greater than 200 feet. If you need some help with calculator instruction, please contact me and we'll look at it together to see if we can figure out how to help. But be very careful that you're keeping up with order of operations with your calculator. Now the last question, again, is really a review of something we've done before. After how many seconds will the ball hit the ground? Well, I know I have this same equation. My question is, what do I know when the ball hits the ground? It's asking me after how many seconds will that happen. I hope you recognize that means I'm looking for t, the time, so that means I should know the height. Well, what would be the height above the ground when it hits the ground? That would be 0. So it will be very similar to the problem we just did, except we will have 0 that we plug in instead of 200. That's going to change our C value, and we will have to go back and do quadratic formula again. So we have A is negative 16, B is 112, this time C is 75, and if I were to plug in to my quadratic formula, remember I've got a plus and I've got a minus. Now here's what we have to be careful on this one. When I plug in one of these values, I'm going to end up with a negative number. And the reason is, if you look at the diagram back up here, we started 75 feet in the air. That means when time was 0, we were at the top of this building. If you were to continue this parabola on, you would be looking at a negative time because the ball would have been on the ground before it went up 75 feet if you extend the graph of the parabola. So that means when we get a negative answer, we're not going to use it. Negative doesn't make sense for time. So instead, as we were to put these values in, oh, sorry, I'm putting in the wrong one here. That's supposed to be 112 for the B values, 112. And then the A value goes right here, negative 16. The C is positive 75. The A is negative 16. What happens when you plug in and you clean up is only one of the values ends up being positive. And that's going to be a time of 7.62 seconds. That will be when the ball hits the ground again. So plug in carefully. Make sure that you're able to use your quadratic equation formula correctly in the calculator, and let me know if you have any questions.